Hello everyone, welcome back to the channel General Intelligence Hub. Today we are going into our second video which is about variance and standard deviation. In the previous video of this series we have seen what mean is and how data is centered towards the mean, and we have also explored different median, mode and distribution plots and how they affect the data and how it all connects to ML at the end. So today we are going to see how variance and standard deviation are going to affect modeling capabilities, and two data sets can still have the same mean but they can still behave completely differently. So we're going to explore such cases in this video. So let's consider two data sets. One is data set A and the second one is data set B. So if we calculate the mean here, both have a mean of 75, but if we see the data, the distance between the lowest and the highest sample is 80 in this case, but here it's only 10. So even though the mean is actually same for these two data sets are completely different in the spread. So the data set B has more spread here. So these characteristics can only be explained with help of variance and standard deviation. Let's go into like what these metrics are and how they can be useful. So here let's say this is our mean, which is usually denoted by the symbol mu, and for a point P, so the distance between these 2 points is simply the deviation. So basically deviation is how deviated a point is from the mean, which is the center of the whole data. The next step is what is variance. So let's consider two data points P1 and P2, and P1 has a D1 of deviation and P2 has a D2 deviation. If we square all these deviations, and average it out with the number of samples in the data, then we get something known as variance. So the thing to note out here is that the deviation is on a sample level, but the variance is on a distribution level. So variance is like a single number that gives you the spread for the entire data, not like a single point that we are picking out here. And what is standard deviation? It's basically simply the square root of variance. So that's standard deviation, and that's how we arrive at that complex formula, which is under root of x minus mu whole square by n, which is the standard deviation. So one thing we'd like to discuss before we move on to distribution plot is that, so why do we actually have to take a square root? Because we are already getting the variance, which is describing the entire spread of the data. So why do we want to take square root of it? If you see, let's say we are dealing with prices here, right? So for the prices data, when we compute variance, it will be let's say the unit of prices is dollar, the variance will be in dollar square, as we are like computing the distance between two data points, which is again in dollar, and then squaring it, right? But when we take a square root of this, we again end up with our same units dollar, so we can do apple to apple comparisons using standard deviation, and that's one of the reason why standard deviation is pretty popular. So the next one is the distribution plot variation. Let's consider two sample distributions. The first one A is very spread out like this, and the second one is B. So just from the plot itself we can infer that this has more spread, and our standard deviation and variance are a measure of spread itself. So the distribution A will likely have more standard deviation and more variance compared to distribution B. So that's how, like, from the distribution plot we can like quickly analyze if the variation of a distribution plot is higher than the other or not. So how does it all connect to ML, right? That's the end goal of it. So let's consider the same example that we discussed in the last video, which is a house price prediction problem. So just to give you all an idea of the terminology that we use in machine learning, we use something known as features, which are basically the attributes of the data which will help us predict the value. The value that we are trying to predict here is simply called as target variable, which is price in this case. And so the two data distributions here are like, so the first one A is completely spread out, and the second one B it's not that spread out. So what is likely to happen in distribution A case is that, so for a square feet of 3000 and number of bedrooms being 4, and for a good location, we get a value like 250K for the house price. And as the data is widespread, we may get to see another data point, which is 3,000 and the 4 bedrooms and for a good location $2 million. What we're trying to infer from here is that when the target variable has a high variance, then similar looking data inputs will likely lead to completely different outputs, which will lead to bad modeling. If the target variable has less variance, then each output can easily be mapped back to the inputs that were given, and the model will likely perform better. So that's the idea of this entire video. If you have any questions, comment down below, and thank you.